Hi, my name is Alex Bras, and today I'll be going over WEC Grid. WEC Grid is our open source Python package that we developed for the integration of marine energy capture devices onto power system modelers. Here, we're looking at our GitHub repository where we store all of our source code and have instructions for installing and citing our software. Here we can look at our documentation page, which will help with getting started, such as understanding how the software works, installation, um, component design, the data we used, any references we have, and also some examples that I'll be going through. Awesome. Let's head over to VS Code where we can look at some of the Jupyter notebooks that we developed so we can help users understand how to use our software. So this is example one. This is just doing a basic simulation on a smaller grid, such as IEEE 14, which is a 14 bus case. One of the first things you have to do when using WEC Grid is setting a database path. Uh, the software revolves around this database for storing um, and pulling model simulations for. So one of the first things I do is you can call database setup database path and append a database to our software. This should only have to be done once per session, and it stores it locally. So in this example, we're running the IEEE 14 bus case using PyPSA as our backend. One of the first things I like to do when loading in a backend and adding a example is reviewing the grid state, making sure everything lines up. So in here we have 14 buses, 5 generators, 11 lines. It looks like our modeler is complete and added, and we have the right case. So for running an example, we can call simulate, and we can even specify a number of steps here. Um, so in this example, which is already ran, we ran 20 steps, and our solve report is giving us no errors. Looks like it ran for 20 steps, ran for about 5.8 seconds, and everything looks good, successful run. And here we can call some of our plotting functions to see how everything went. We're expecting no news here, some pretty boring simulations because there's no changes to generation or load, so everything just should be steady state, which is what we're seeing here. So we can look at generators, the all constant. In addition to plotting generators, we can also plot our grid using our single line diagram uh, plotting call. So moving on to a more advanced example, we can look at example 3, which is adding a WEC farms and with the load curve to a grid example. So here we're looking at IEEE 39, same backend using PyPSA, and we're going to apply a couple WEC farms to our grid. Looking at the database as a reference, we can look at what WEC-Sim runs we have in the backend. I'll go into running a WEC-Sim run in a minute, but here we can look at what WEC-Sim runs are already in the database. So it looks like we have 2 with the IDs of 1 and 2, and one is a Lupa type, and the other is an RM3. And we can have our specifics or the specific configurations of those WEC-Sim runs here. Uh, Now we can apply those WECs to our grid using apply WEC. And here we're giving them a name, and we're using the sim ID that we pulled from uh, uh, this WEC-Sim runs call. So we're adding a Lupo with the ID of 2, an RM3 farm with the ID of 1. And we can even add how many devices we want per WEC farm. So we added those farms. One of the things I like to do is review some of the data that's on those farms. So here we're looking at the first RM3 farm and the Lupa farm. We can see that we have our sim ID, how many devices are on there, bus location, and connecting bus location. And we can even review the data from one of the devices on the farm. So we can see the active power from the RM3 here, and we can even pull the wave elevation data to see what kind of run, uh, what kind of waves were applied to this WEC. Same here for the LUPA. We can look at the power from the LUPA and the wave elevation. And now with those appended, we can look at the grid state, and we see that we do have 42 buses and 13 generators, which is an increase from the baseline IEEE 39 bus. That's because we added those new components. We can review what our grid looks like using the SLD. I know this one looks a bit funky. There's a bug with the SLD plotting function. Um, and now we can apply a curve, a load curve specifically to our grid using this generate load curve function. WEC Grid looks at all the loads on the grid and applies a two peaking day to that grid. So here we see around 7 a.m. we're getting an initial peak, and around 5 p.m. we're getting another peak. Uh, this is just to simulate some real world conditions to get a better understanding of this actual integration. So now we can run a simulation by calling simulate. We say that we do have a load curve, and we can look at the report after. This took some time. This took about 2 minutes to run, but we see that it solved successfully. Um, in addition to wanting to see how the grid performed, we also want to see how the simulation performed. So looking at a report, we can see how long each iteration took. We can see how many iterations of the powerful solver it took to complete a convergence. We can even see how long it took to pull data from the backend as well. So here I plotted a few of those things, such as iteration time, powerful time, and snapshot time. And things look perfectly normal, really good to me. And now we can pull, or we can plot that simulation here. So we can plot our bus data. So bus 31 would be our swing bus. We can plot our WEC buses, and we can even pass a parameter that we want to look at, such as voltage magnitude. Everything looks great. We also have a specific call called WEC analysis, which creates these three plots to look specifically at how the WECs perform on the grid. So we can see generators here, we can see power contribution specifically from the WECs, and then bus voltage. Everything looks great to me. Um, Moving on to another aspect of the software is interfacing with WEC-Sim or doing a WEC-Sim run. Um, so we built a wrapper around WEC-Sim called WEC-Sim Runner that we can call to do WEC-Sim runs without actually opening up MATLAB. So we can import our WEC grid, initiate a new object, and set a path to WEC-Sim. So here I have my path to my WEC-Sim, and I do a show config to make sure everything's set up correctly. And then here is the actual model, or the simulate call that we pass over to WEC-Sim. If you ever use WEC-Sim, a lot of these parameters look extremely similar, where you can pass like a wave class, wave height, period, seed. And important here, we're passing a model location as well. So this is what the output would look like. We get a little wave, and we get to run our simulation. We collect that information back, and WEC-Sim, we have a user-defined function in WEC-Sim that places it back into our database. And it gives us a quick plot with the active power in watts over, and then on the right axis, y-axis, we have our wave elevation. Awesome. Moving over to example 4, one of the other aspects of this is that we can compare our open source backend modeler, which is PyPSA, to PSS E, which is our commercial solver. And in this example, we're looking at RTS96, which is a much larger case, and we're running the PyPSA background. Here we can see what that grid would look like, and we're applying a WEC farm here. We're applying an RM3 WEC farm with 10 devices at bus 326. We do our simulation, everything looks great to us, and we do our plots, and here we kind of see iteration time, powerful solver time, and snapshot time. One of the great things about using this database as this focal is that we can store our simulations from WEC Grid and WEC-Sim and pull those in later. So here we're querying the database to look at grid simulations that we have. And in our database, we have some preloaded ones of PSSE. And here we have two. We can see we have PSSE RTX GMLC, which is our 96 case that we just ran. And it looks like we have one with the WEC farm on it, and we have one just a baseline. The beauty of this is if you don't have access to PSSE, you can still run a similar example using the open source modeler and then pull in that data from the database and do a comparison. You won't need to run your own PSSE runs. So this is what we're doing here, is we're looking in the database. We see that we have some PSSE ones that we can compare with, and we do a pull sim. And in the example, but now that we pull that in, we can look at our PyPSA grid, look at our bus data, and the same thing here. We can look at our PSSE grid, and we can look at our bus data. Um, these were the exact same setup for the simulation. And here we add our grid to our example. So we have a software PSSE and we pass in that grid state. And then now we can do some plotting actually. So you can see here that in plot we can pass a backend that we want to look at. So PSSE or PyPSA, and we can see how the grid performed. So you can notice up here in the top of the titles that we have PyPSA running our simulation. We're looking at active power and per unit over time. Things look pretty great. Very similar to PyPSA. Here in PyPSA we have our active power at our WEC bus here. Looks extremely similar. Looks like things are in agreement here. Um, and right, here are some additional plotting functions that we have. We have the ability to compare the modelers directly on the same plot. So we're looking at bus, and we're looking at this bus 326, which is our WEC bus. Also looking at bus 123 and 113. It looks like things exactly line up. It's maybe difficult to see, sorry about that, that they're overlapping quite a bit, which is what we want to see because we're hoping the integration exactly the same. We can also pull some RSME values, ape values, mean, things like that. And those are printed out when you run those. Uh, it looks like the bus 123 is in relative agreement. There's some differences there. And the same for bus 113. Perfect. I hope these examples help you understand how what grid works. Yeah, and thank you so much for your time.